Hey everyone, welcome back. You know how much I love getting into the nitty-gritty of materials, so I'm really excited for today's deep dive.
Oh, yeah, this is a good one.
We're tackling a chapter on the optical properties of materials, which is basically the science behind why things look the way they do.
It's something we experience constantly, but probably don't think about that much.
Exactly. Like, have you ever wondered why metals are so shiny?
Or why a ruby is red, but a pure sapphire is clear.
Or why you can't see through a penny, but you can see right through a window?
All those everyday things come down to how light interacts with different materials, all the way down at the atomic level.
And to help us unpack all of that, I've got an expert with me who can explain the why behind the what. Welcome. I'm so glad you could join us.
Glad to be here. It's a topic I'm really passionate about.
Awesome. Okay, so the chapter starts with the basics of electromagnetic radiation, which, I'll be honest, always makes my brain go a bit fuzzy.
Yeah, it can be a bit abstract, right?
Totally. Is
Mm.
there a simpler way to think about it?
Sure. Think about it like this. When you toss a pebble into a pond, what happens?
You get those ripples spreading outward, right?
Exactly. Those ripples are carrying energy outward from where the pebble landed.
Okay, I see where you're going with this.
Electromagnetic radiation is kind of like that. It's energy traveling through space. But instead of water moving up and down, it's electric and magnetic fields oscillating.
So it's like invisible ripples of energy.
You got it. And just like those ripples in the pond, electromagnetic radiation comes in different wavelengths, which is basically the distance between the peaks of those waves.
Right, and visible light is just one tiny part of that whole electromagnetic spectrum, right?
Exactly. There's that classic illustration showing the whole spectrum, from radio waves to gamma rays, and visible light is this minuscule sliver in the middle.
Yeah, they compared it to finding a specific grain of sand on a beach.
Which is pretty crazy when you think about it. All this invisible energy is all around us, and we can only see a tiny fraction of it.
It's like we're missing out on a whole other world.
Right. It makes you wonder what it would be like if we could see all those other wavelengths.
Seriously, the world would look totally different. But okay, even sticking with visible light, it gets even weirder when we start talking about photons, right?
Oh, absolutely. Photons are like these tiny packets of light energy.
And they're kind of mind-bending because light doesn't just act like a wave, it can also behave like a particle.
Exactly. It's that whole wave-particle duality thing, which can be a bit hard to wrap your head around.
Totally. But the key takeaway is that the energy of a photon is directly related to its frequency. Higher frequency means higher energy, which explains why ultraviolet light can give you a sunburn, but radio waves can't.
Right. It all comes back to those tiny photons and how much energy they're carrying.
Okay, so all this talk about photons makes me think about solar cells. You know that picture in the chapter showing a house with solar panels?
Yeah. Solar cells are a great example of how we can harness the power of those photons.
I've always been curious about how those panels actually turn sunlight into electricity,
Well, it all comes down to the photoelectric effect.
which is basically what we were just talking about, right? Light knocking electrons loose.
Exactly. So when sunlight hits a solar panel, the photons interact with the material inside, typically silicon, knocking loose electrons and creating an electric current.
So every time I see a solar panel, I should picture all those little photons doing their work.
Pretty much. It's fascinating to think about, but it does make you wonder, if energy comes in these tiny packets called photons, is it truly quantized?
What do you mean by quantized?
Well, could we have like half a photon? Or is it always these discrete packets of energy?
That's a great question. I'm not sure. Maybe something for our listeners to ponder.
Exactly. Okay, but let's move on from photons for now and talk about how light interacts with solid materials. The chapter breaks it down into four main ways: transmission, absorption, reflection, and refraction.
Right, and they use the example of looking through a tinted car window, which I thought was really helpful.
Yeah, it shows how all four interactions can happen at the same time.
Exactly. So with a car window, you can see through the glass, meaning some light is being transmitted.
But the tint also means that certain wavelengths of light are being absorbed, giving it that specific color.
And you can also see a faint reflection of yourself in the glass.
Plus, if you look closely, the objects outside appear slightly distorted because of refraction.
Right, because the light is bending as it passes from the air into the glass.
Exactly. And the amount that light bends depends on the material's index of refraction.
So materials with a higher index of refraction bend light more dramatically. I remember the chapter mentioned that lead is added to glass to make crystal sparkle more.
That's right. Those lead ions are larger and denser, so they increase the glass's index of refraction.
And that makes the light bounce around more inside the crystal, creating that sparkle.
You got it. It's all about how the material structure affects the way light interacts with it.
Okay, so we've talked about transmission, absorption, reflection, and refraction. But what I'm really curious about is why metals are so shiny.
Ah, yes, that metallic luster. It all comes down to the way metals are structured at the atomic level.
I have all those free electrons bouncing around right, like a crowded dance floor. I loved that analogy from the chapter.
It's a perfect way to visualize it. So when light hits a metal, those free electrons can easily absorb the photon's energy.
And then they re-emit those photons, which is what we see as that shiny reflection.
Exactly. Most of the absorbed light energy is re-emitted as the same color, but a tiny bit is lost as heat, which is why metal objects get warm when you leave them out in the sun.
That makes sense.
Hmm.
But not all metals are silver-colored, like gold and copper. Why is that?
Good point. It's because they don't reflect all wavelengths of light equally. Gold and copper absorb some blue and green light, so what we see is the reflected light minus those colors, giving them those warm, characteristic hues.
So it's like subtracting colors from the reflection. That's so cool.
It is, and it all comes back to those subtle differences in how different materials absorb and re-emit light.
It's amazing how these tiny variations at the atomic level can create such a huge difference in what we see. But okay, we've talked about metals, but what about nonmetals?
Ah, well, they're a whole other story.
Because they can be shiny too, but they can also be transparent. So things must work a bit differently, right?
You're right. With nonmetals, it all comes down to the size of their band gap.
The band gap. Remind me what that is again.
Right, so in simple terms, it's the energy difference between the valence band, where electrons are bound to the atoms, and the conduction band, where they're free to move around and conduct electricity.
Okay, so the band gap is like an energy hurdle that electrons have to overcome.
Exactly. And the size of that gap determines whether a photon of light has enough energy to excite an electron and be absorbed.
The chapter compared it to trying to jump over a hurdle. If the photon has enough energy, it gets absorbed. If not, the light passes right through, making the material transparent.
Perfect analogy. And the size of that band gap also determines a material's color. For example, diamond is transparent to visible light because its band gap is so large that no visible light photon has enough energy to be absorbed.
So that's why diamonds are clear. It's like a hurdle that's too high for any visible light photon to clear. But wait, the chapter also mentioned that diamond is opaque to ultraviolet light. How does that work?
Great question. It's because ultraviolet light has a higher energy than visible light, so even though the diamond's band gap is large, those high-energy UV photons still have enough energy to excite those electrons.
Gotcha. So it's all about the energy of the photon relative to the size of the band gap.
Exactly.
And speaking of band gaps, the chapter also explains how impurities can create energy levels within the band gap, which can affect a material's color.
Right. They use the example of ruby and sapphire, which are both forms of aluminum oxide.
Yeah. Ruby gets its red color from chromium ions, creating specific absorption peaks within the band gap, while pure sapphire has no such impurities and is therefore colorless.
It's a perfect example of how a tiny amount of impurity can dramatically change a material's optical properties. And the transmittance graph in the chapter really illustrates this difference beautifully.
It's mind-blowing how these subtle changes at the atomic level can have such a big impact on what we see.
Totally.
Yeah.
But even inherently transparent materials can become translucent or opaque.
Right? And that's because of scattering, like when you shine a flashlight beam through fog.
Exactly. The light gets dispersed in all different directions, making it hard to see clearly.
And the chapter lists 4 main sources of scattering: anisotropic indices of refraction, two-phase materials, pores, and highly crystalline polymers.
So basically anything that disrupts the path of light within the material can cause scattering.
Like a bunch of tiny obstacles that the light has to bounce around. So the next time I see frosted glass, I'll know it's those tiny internal structures scattering the light.
Exactly. It's all about understanding how light interacts with the structure of the material.
This is all so fascinating. Okay, we've talked about the why behind color and transparency, but the chapter also covers some amazing practical applications of these optical phenomena.
Oh, absolutely. There's so much we can do when we understand how to control how light interacts with materials.
Like luminescence, which is the ability of a material to absorb energy and then re-emit it as visible light.
Right. And there are 2 main types of luminescence: fluorescence and phosphorescence.
The difference is how long that re-emission takes, right?
You got it. Fluorescence happens almost instantly, like a glow-in-the-dark toy. But phosphorescence can last much longer, like those glow-in-the-dark stickers you might have had as a kid.
Oh yeah, I remember those. They'd glow for hours after you turned off the lights.
Exactly. And then there's electroluminescence, which is how LEDs work.
Right. Instead of using heat like an incandescent bulb, LEDs use electricity to create light.
Yep. An LED is basically a p-n junction, which is a special type of semiconductor device. And when a voltage is applied, electrons are injected from the inside to the p side, releasing energy as photons and creating light.
It's amazing how we can create light by applying a voltage to certain materials.
It is. And by using different semiconducting materials, we can create LEDs that emit different colors of light, which is why they're now used in everything from digital displays to traffic signals to home lighting.
It's incredible how LEDs have transformed our world.
Totally. But we can't forget about photoconductivity, which is another fascinating phenomenon.
Remind me what that is again.
It's the ability of certain materials to become more electrically conductive when exposed to light. It's like light can act as a switch, turning on the flow of electricity.
Oh, right. And the chapter explains how this is used in photographic light meters to measure light levels.
Exactly. The amount of current generated is proportional to the intensity of the light hitting the sensor, allowing photographers to determine the proper exposure settings.
So clever. Okay, so we've covered luminescence, photoconductivity, and LEDs. What else should we talk about?
Well, we can't forget about lasers. These devices create incredibly focused beams of light through a process called stimulated emission.
Right, and they've revolutionized countless industries.
Absolutely. Lasers are used in everything from surgery and manufacturing to barcode scanners and telecommunications.
And they're based on a really cool principle, right?
Yes. It's called stimulated emission. The chapter uses the ruby laser as an example, where a flash of light excites electrons in the ruby crystal. And then those excited electrons release their energy as a synchronized burst of photons, creating that intense, coherent beam of light that we know as a laser.
Wow, that's incredible. Okay, so we've covered lasers, but there's one more application we needed to talk about. Optical fibers.
Ah, yes, those thin strands of glass that have transformed the way we communicate.
It's amazing to think how much data they can handle. I remember reading that a single optical fiber can carry as much information as a massive weight of copper wire.
It's truly remarkable, and it all comes back to those fundamental optical properties we've been discussing.
This whole chapter has been a real eye-opener for me. I never realized there was so much to learn about light and how it interacts with materials.
Right. It's a field that's both fascinating and incredibly impactful.
Absolutely. And we've only just scratched the surface.
There's so much more to explore, and I'm excited to continue this deep dive with you in part 2.
Me too. We'll be back soon to uncover even more amazing things about the world of optics.
Welcome back to our deep dive into the fascinating world of optics.
I'm still buzzing from all the incredible things you learned in part 1. It's amazing to think about how much we've covered already, from the fundamental nature of light itself to how it interacts with metals and nonmetals.
And we've just begun to scratch the surface of the practical applications. Those examples we discussed, like LEDs and solar cells, really showcase the power of understanding optical properties.
It's like unlocking a whole new level of understanding about the world around us. Speaking of those incredible technologies, let's pick up where we left off with optical fibers.
You mean those thin strands of glass that have revolutionized the way we communicate?
Exactly.
Yeah.
I'm still a little fuzzy on how they work. How can light travel such long distances through those tiny fibers without losing signal strength?
It all comes down to a remarkable phenomenon called total internal reflection. Imagine a beam of light traveling through the core of the optical fiber.
Okay, I'm picturing it. The core is that central part of the fiber, right?
Yes, and it's surrounded by a layer called the cladding, which has a slightly lower index of refraction.
That difference in refractive index is crucial, isn't it?
Absolutely. When the light beam hits the interface between the core and cladding at a shallow angle, it gets completely reflected back into the core. It's like a mirror, but instead of reflecting light from the surface, it's reflecting it from the inside.
So the light beam is basically bouncing back and forth within the core, traveling down the length of the fiber like it's trapped in a mirrored tunnel.
You got it. And because the cladding prevents any light from escaping, the signal can travel incredibly long distances with very little loss of intensity. It's like a superhighway for light with no traffic jams or detours.
That's a fantastic analogy. But the chapter also mentions something about different types of optical fiber designs. Step index and graded index. What's the difference?
That's where things get a bit more nuanced. In a step index fiber, the refractive index changes abruptly between the core and the cladding, like a sharp step down.
And this can cause problems, right? The chapter mentions something called pulse broadening.
Yes, unfortunately. Because different light rays travel slightly different paths within the core, they arrive at the end of the fiber at slightly different times. This can blur the signal, especially over long distances, making it harder to decode the information.
So how do we solve that problem?
That's where graded index fibers come in. In these fibers, the refractive index changes gradually from the center of the core outwards. It's more like a smooth slope than a sharp step.
And that makes a difference.
A huge difference. The gradual change in refractive index causes the light rays to bend in a curved path. So even though they travel different distances, they arrive at the end of the fiber at roughly the same time.
So it's like a race where everyone gets a head start based on their lane position. So they all finish at the same time, even though they're running different distances.
A perfect analogy. This clever design minimizes pulse broadening, allowing for much faster and clearer data transmission. And that's essential for modern telecommunications, where speed and accuracy are paramount.
It's fascinating how engineers have fine-tuned the design of optical fibers to achieve such incredible performance.
It truly is a testament to human ingenuity. But it all comes back to understanding the fundamental optical properties we discussed earlier, and let's not forget the crucial role that materials play in this technology.
Right, the chapter emphasized the importance of purity when it comes to optical fibers.
Absolutely. Even tiny amounts of impurities can scatter or absorb light, reducing signal strength and clarity. It's like having potholes and roadblocks on our light superhighway.
The chapter specifically mentioned copper, iron, and vanadium as major culprits. They also said water and hydroxyl ions can cause problems.
Those are the usual suspects. They can wreak havoc on signal transmission. That's why manufacturers go to extraordinary lengths to create ultra-pure silica glass for optical fibers.
The chapter mentioned that the power loss through 16 kilometers of optical fiberglass is equivalent to the loss through just 25 millimeters of ordinary window glass. That's a staggering difference.
It's a testament to the purity and precision of these materials. And we can't overlook the importance of uniformity in the fiber's dimensions. Even slight variations in diameter can affect light transmission, making consistent manufacturing a critical factor.
So we're talking about tolerances on the order of micrometers over kilometers of length. That level of precision is mind-boggling.
It is, isn't it? But that's the level of detail required to ensure the remarkable performance of optical fiber systems. It highlights the incredible advancements we've made in materials science and engineering.
Well, after learning all this, I have a newfound appreciation for the complexity and sophistication of optical fiber technology. It's one of those everyday miracles that we often take for granted.
I agree. It's easy to forget the intricate science and engineering that make our connected world possible. But speaking of everyday miracles, we haven't even scratched the surface of all the other applications of optics.
Right. We've talked about LEDs and lasers in communication and lighting, but the chapter hinted at so much more. What are some other fields where optics plays a crucial role?
Well, medicine is a great example. Lasers are now routinely used in all sorts of surgical procedures, from delicate eye surgery to targeted tumor removal.
That's right. Lasers can make incredibly precise incisions, minimizing damage to surrounding tissue. And because they cauterize as they cut, they reduce bleeding too, which speeds up healing. It's a game changer for many surgical procedures.
And their applications in medicine go beyond surgery. Lasers are also used in various diagnostic tools, like those used to measure blood flow or analyze tissue samples. Optical imaging techniques like MRI and PET scans allow us to see inside the human body without invasive procedures.
It's incredible how optics are used to both diagnose and treat medical conditions, leading to earlier detection, more effective treatments, and better outcomes for patients. But I bet the applications go far beyond medicine, right?
Absolutely. Manufacturing is another great example. Lasers are used to cut, weld, and engrave materials with incredible precision and speed. Think about the intricate designs on smartphones or the complex circuitry on computer chips. Lasers play a vital role in creating those.
It's hard to imagine modern manufacturing without lasers. And let's not forget about some of the more everyday applications, like barcode scanners, laser pointers, and even those CD and DVD players we used to use.
Right. And we can't overlook holography, which uses lasers to create those amazing three-dimensional images. Remember those holographic stickers we used to love as kids?
Oh yeah, those were so cool. But holography isn't just about childhood nostalgia. It's also found practical applications in data storage and security.
Exactly. Holograms can store a vast amount of information in a tiny space, and they're incredibly difficult to counterfeit, making them ideal for security applications.
It's clear that lasers have revolutionized many industries. But the innovation doesn't stop there. What are some of the emerging trends or exciting new applications that we might see in the future?
That's a great question. The field of optics is constantly evolving, with researchers developing new types of lasers and finding innovative ways to use them. One area that's particularly exciting is the development of self-driving cars that use lasers to map their surroundings and navigate safely.
That's right. Those LiDAR systems, which stand for light detection and ranging, are crucial for autonomous vehicles to perceive their environment. It's mind-blowing to think that lasers are helping to shape the future of transportation.
And let's not forget about quantum computing. This revolutionary technology relies on the principles of quantum mechanics to perform calculations that are impossible for classical computers. And guess what plays a key role in quantum communication and information processing?
Light, of course. It's the perfect medium for transmitting quantum information.
Exactly. So, as quantum computing continues to develop, we can expect to see even more fascinating applications of optics in this cutting-edge field.
Wow, this is incredible. From self-driving cars to quantum computers, it's clear that optics will continue to play a crucial role in shaping our technological future.
Absolutely. And it all stems from that deep understanding of the fundamental optical properties we've been discussing throughout this deep dive. It's a testament to the power of scientific inquiry and the incredible potential of light.
This deep dive has been a real eye-opener for me. It's given me a whole new perspective on the importance of optics in our world.
Me too. It's a field that's both fascinating and impactful, touching on everything from the fundamental nature of light to the technologies that are shaping our lives and our future.
And there's still more to come. We have one more part of this deep dive to go. Join us as we wrap things up and explore some final thoughts on the fascinating world of optics. And we're back for the final part of our deep dive into the optical world.
It's been quite a journey, exploring how light behaves and interacts with all sorts of materials.
We've covered so much ground, from basic principles to mind-blowing applications.
And now we're ready to wrap things up with a focus on one of the most exciting areas of optics: how light can be used to create energy.
You're talking about solar cells, right? Those incredible devices that convert sunlight into electricity.
Exactly. Solar cells are a prime example of how manipulating those optical properties can lead to game-changing technologies.
So let's break it down. How do these magical devices actually work? How do they transform sunlight into usable electricity?
Well, at the heart of it all is a semiconductor material, usually silicon. When sunlight hits the solar cell, the photons in that light interact with the silicon atoms.
Okay, and what happens then?
Those photons, those little packets of energy, knock loose electrons from the silicon atoms. It's like the photoelectric effect we discussed earlier, light freeing those electrons.
Ah, right. And then those freed electrons create the electric current.
You got it. Those electrons flow through an external circuit, generating the electrical energy we can use to power our homes, businesses, and, well, pretty much everything.
It's like pure magic sunlight turning into electricity. But I imagine there are challenges, right? Are there energy losses during this conversion, and how can we minimize them?
Absolutely. Great question. You've hit a key point there. It's a complex process, and yes, there are always energy losses involved. The efficiency of a solar cell, meaning how much sunlight actually gets converted into usable electricity, depends on several factors.
Like the material itself, right?
Yes, the material is crucial. Remember those band gaps we talked about?
Those energy hurdles that electrons have to overcome.
Exactly. The band gap needs to be just right to absorb the most energetic photons from sunlight. Too large, and the photons won't have enough energy to excite the electrons. Too small, and those excited electrons might lose their energy too quickly.
So it's a delicate balance, finding that Goldilocks band gap for optimal efficiency.
Precisely. And it's not just about the material itself. Scientists are constantly exploring new designs and structures to capture as much sunlight as possible and minimize energy loss.
I know there are different types of solar cells out there, each with its own pros and cons. Can you tell us a bit more about those?
Of course. The most common type is the crystalline silicon cell. They're pretty efficient, but the manufacturing process can be a bit pricey and energy intensive.
And then there are those thin film solar cells, right?
Yes, those are generally cheaper to produce because they use less material. but they're typically less efficient than the crystalline silicon ones.
The chapter also mentions some newer cutting-edge technologies like organic solar cells and perovskite solar cells. What's the deal with those?
Those are some really exciting areas of research. Organic solar cells use carbon-based materials, which are potentially cheaper and more flexible. And perovskite solar cells have shown some impressive efficiency gains recently, even rivaling those traditional silicon cells.
It's incredible how the field of solar energy is constantly pushing the boundaries. What drives this relentless pursuit of better solar cells?
It's a combination of things, really. The urgent need to find cleaner energy solutions to tackle climate change is a huge motivator. Plus, there's that inherent drive to develop better technologies, things that are more efficient, more affordable, more versatile.
And solar energy seems to tick all those boxes, right? Clean, renewable, and constantly improving.
Absolutely. As the technology keeps getting better and costs come down, solar energy is becoming a major player in the global energy scene. It's already powering homes, businesses, even entire cities. The potential is huge.
This whole deep dive has been an eye-opening experience, to say the least. I had no idea how much we rely on optics in our everyday lives, from simply seeing to these complex technologies like solar cells.
It's amazing, isn't it? We've seen how light interacts with matter in so many ways, from creating the colors we see to generating clean energy. It's a field that's both fundamental to our understanding of the universe and critical to developing those innovative technologies that shape our world.
I hope our listeners have enjoyed this journey as much as we have. It's been a fascinating exploration of the power and beauty of light.
I agree. It's a testament to the wonders of science and the incredible things we can achieve when we delve deeper into the world around us.
And on that note, it's time to wrap up our deep dive into the optical world. Thanks for joining us, everyone, and we'll catch you next time for another exciting adventure into the realm of science and technology.